Good evening. This is the voice of Satish, and I will be the facilitator for today's session. Today's session is brought to you by Young Scientist. This is level 2 of the Brain Excel series of workshops. And today's topic is pattern recognition. I hope you guys had the chance to read the quote on the screen that was left there for some time by Mr. Whitehead. And he talks about patterns in art and the enjoyment of art. Art is the imposing of a pattern on experience, and our aesthetic enjoyment is the recognition of the pattern. If this idea does not make sense to you, I encourage you to think about it later. It might take a few hours or many days or even a few years for you to completely appreciate the insight that this sentence provides. We will be dealing with the idea of patterns today. And we will be trying to develop skills that helps us to recognize those patterns. Although we will not be dealing with art, these skills can be translated to an analysis of art. Classical thinkers believed that the foundation of everything is mathematics. Let's take, for instance, this beautiful image that you can see. An open question to everybody. Can you recognize this image? Do you know what it is? It is not an image generated by a kaleidoscope. However, there is some similarity between an image of a kaleidoscope and what you see here. What you're witnessing here is a graphical representation of a mathematical object. I'm quite surprised that none of you have been able to identify this. Even if not by name of this particular image, this class of images are known as fractals. Let me type that word for you. Yeah. Now, from the outside, it looks like a beautiful artistic image. But if you analyze this, the entire image comes from a simple mathematical equation. And if you look closely, you will find that there is a repetition or a pattern to be discerned from this image. This particular fractal is known as the Mandelbrot set, named after the mathematician who discovered the fractal. Now, the significance of this fractal, the Mandelbrot set, fractals in general, is very dense. We will not be dealing with that today. This image is here to show you that the foundation of art and complex images can be simple mathematical equations. If you're wondering what a fractal is, a simple definition is it's a geometrical figure that has a finite surface area, but and an infinite an infinite circumference. All right, let's continue with our discussion of pattern recognition. We find patterns everywhere, especially in nature. And that's why the ability to recognize and analyze the patterns is quite important. Where do we find patterns in nature? Here we see the image of a sunflower. And you're looking at the seeds of the sunflower. And if you have a bit of imagination, you can see that they seem to form a spiral. And in fact, mathematicians have studied the geometrical patterns in the sunflower seeds. Now here we see the pattern that emerges from a flower that has 1,000 seeds. It might be a Fibonacci spiral. It's one of the explanations for the pattern, but there are other solutions too. Now, removing the seeds, you can see a combination of spirals. It's not a simple spiral, it's not a single spiral, but there are several spirals. There's a repetition of spirals here. There's the pattern with blue lines and also the pattern with red lines. Now, with 3,000 seeds, the pattern becomes more complex, but also more pronounced. There seems to be some irregularities in the center, but as you move out away from the center, you see these lines, the arms of the spiral, quite distinctly. Now, another pattern sorry about that. Looks like I got briefly disconnected. As I was saying, another type of pattern that you can find in nature, besides the spirals, is that of a tessellation. Those of you who joined us for one of the RoboCompass sessions would be familiar with the idea of a tessellation. It is the arrangement of geometrical shapes, especially polygons, like squares, triangles, octagons, pentagons, whatever, in a repeated pattern without overlapping or having any gaps between the objects. Can you guys give me an example of the tessellation pattern in nature? Yeah, very nice. A mosaic or a beehive. I cannot think of any flower that has a tessellation pattern, but yes, the beehive is the best example of a hexagonal tessellation pattern found in nature. If you study engineering later, you will learn that this close arrangement of hexagons is one of the most structurally stable that can be designed. If you look around, chances are that you will find tessellation patterns around you. Maybe in your clothing, on your floor. If you have a wallpaper, then wallpapers generally have repeated designs. Tessellation is also found in architecture. Here we see a tessellation of triangles or squares, or whatever you want to recognize this shape as. This is the famous Epcot Center, which can be found in one of the Disneyland, which is technically a biosphere which uses a tessellation pattern on its surface. Yes, this is three-dimensional, and it would be a tessellation of pyramids. Okay. Here's a closer look of a different dome that has tessellation of irregular triangles. Here's yet another example of a tessellation pattern. Tessellation is also found in art. Here we have an overlapping image of a lizard. Although the orientation changes, the color changes, these are exact, identical images. It's a repetition of the same drawing of a lizard. Here is an abstract art, which is also a tessellation. It gives an illusion of having boxes, three-dimensional boxes that are stacked in some strange, weird ways. You can also animate tessellation patterns to create a moving image. I think the image says it all as to what's going on here. The gap between the black cats turn into a dove, and each dove flies away. If you're very creative, you can also create an infinite zoom, so to speak. And in this case, we have a tessellation pattern of elephants. All right, so I have an open question. Where else do we find patterns? In mathematics, yes, sure. You will see a lot of that later. Drawings, paintings, monuments, okay? That's like art and architecture. Flowers, okay. Architecture is fine. Walls, all right. But how about this? Where else do we use patterns? In geometry, jewelry, very good. In design, yes. Okay. Now, patterns and recognition of patterns is quite integral to a field of communications. A surreptitious type of communication, secret communication. Yes, a Morse code is one type of cryptography where we encrypt a message. When we encode a message into what might seem like nonsense to a stranger, but to the recipient, to the person to whom you want to send the secret message, they can decode or decrypt that message, okay, and get the hidden message inside. Now, the use of cryptography and cryptic messages dates back to ancient times. Historically and famously to the time of Julius Caesar and Caesar's cipher. Now here's an example of how a secret message can be decrypted. Now at the top, you see what looks like a garbled text, but by slowly, gradually deciphering it, and there are many methods of doing it, you can get to the hidden message. And this process of deciphering, decoding the secret message involves recognition of patterns. Let's take the Caesar cipher, for instance. Now this is a simple example of letter substitution. By replacing every instance of the letter D in your message with, say, A, for example, and E with B, and F with C, and so on, until you come back to A, which will be X, and B will be Y, and C will be Z. You have a method of translating a normal message into a string of nonsense. And then when you're trying to decode it, the best way to do it is to use trial and error. You guess at these substitutions, and then you look for patterns when you decode. Then eventually you'll come to what is known as the key and break the code. That's Caesar wheel. Now, the practice of cryptography was never more famous than during the World War II, when the Nazi Germany used an innovative machine known as the Enigma Machine. We have a photograph of one such machine here. And with this, German military officers could send secret messages to each other through telegram by directly typing into this machine. And the recipient will simply have to use a similar machine to decode that message. This was a big problem to the Allied forces, or the good guys. And as long as the Germans had this method of communicating in secret, the Allied spies were unable to get intel or military intelligence. Those of you who have an interest in war would know that espionage or spies like James Bond, or from modern times, you could say Ethan Hawke or Jason Bourne. Yeah, the people who are spies who try to get secret information. Ethan Hunt, thank you. So those guys would have a big trouble because they will only get the secret messages, but they would have no idea. The governments, the military people have no idea how to get the original message. So you have to break this code. You need to unlock the Enigma machine. Do you guys know who actually did that? Who broke the Enigma code? Very good. It was Alan Turing, a mathematician. In fact, recently a film was released about Mr. Turing. You might also recognize him as the person who invented the Turing test in artificial intelligence. He was a mathematician and a genius. And when he was very young, in his 20s, he was able to find a method, find the patterns in the secret messages that Germans were communicating with. And he broke the Enigma code. And almost single-handedly, he was able to turn the tides of war. He was instrumental in contributing to Allied victory. So yeah, mathematics and pattern recognition can change the course of history. You also find patterns in music. The simplest explanation would be a rhythm. A rhythm is a repetition of certain sounds. Without that repetition, we would have noise. Now, some of you may be studying music and the theory of music. Some of you may not. In any case, I'm going to show you the Western classical notation of music. And even if it doesn't make sense to you musically, you can see that there is a repetition here. Right? There is a group of shapes that gets repeated. Now, each black dot here represents a note in music and a particular sound. And a group of notes represent a piece of the melody. Now, even a layman can see that there is a pattern here. Now, on the left-hand side, you have a piece of music. And while looking at it seems unintelligible to someone who doesn't have training in music notation. But if you look closely, you can see that there is a repetition of pattern here. I have highlighted only a few patterns. There's more for you to discover. You can see that all those highlighted in yellow, blue, and the different colors represent a repetition of a relationship between the notes. So the next time you listen to your favorite song, try to listen closely and recognize any patterns you might notice. Or if you have a favorite genre of music, be it pop or rock, whatever, look at the different songs and try to see similarities between the songs. The similarities could be abstract, or it could be as simple as the use of common instruments. You can even find patterns in films, in stories. For example, most of the Disney stories and fairy tales end with the main characters living happily ever after. And most of the fairy tales start with once upon a time, long, long ago, in a faraway place. Now, that is a literary trope, a pattern that's repeated across thousands and thousands of stories. If you look at Tamil films, well, I'm sure there's plenty of patterns to recognize there. And once you get good at it, you'll be able to not only appreciate good art, but also be able to identify art that takes shortcuts. You also have behavior patterns, especially in animals. On the left-hand side, you see migrating birds. And migration is a pattern, a behavior pattern that birds exhibit every year. These patterns are learned, or it can be instinctive. In the case of the ducklings, they learn these behavior from their mother, usually, by imitating them. This is known as imprinting. I mean, who teaches a dog to bark? Who teaches a duckling to quack? Or who teaches a hen to incubate its eggs. These are patterns in behavior that get transmitted either through imitation or through genetic transmission. In this image, we see a pattern of roots of migratory birds. So every year, when you track the movement of birds of particular species, you will find that they follow this route. And then you might even see a normal trend. They move from north to south to escape the winter. And sometimes if they are birds from the cold regions, they move from one pole to the other pole. So when winter becomes intolerable in one place, they move to the other pole where the winter is not so bad. So recognition of patterns has a lot of use, from art, from architecture, in cryptography, secret messages and stuff, in music, in the study of human and animal behavior as well. I mean, why don't you take some time and study yourself? What do you do every day? What kind of actions do you repeat every day? All right, it's now time for some mathematics, because through mathematics we can develop the tools needed to analyze complex images, sounds, shapes, and so on. So mathematics is a good place to learn pattern recognition. So the best way to represent a pattern is through numbers. And numbers can form sequences and series. It's important to understand the distinction between those two. A sequence, well, it's a sequence of numbers, one after the other. Okay. A series is when you add the individual terms of a sequence. Okay. There are several sequences of numbers. One of the famous sequences in mathematics is the Fibonacci sequence. The prime numbers, they form another sequence, something that we have not been able to decode or crack. We don't know what pattern the prime numbers follow. Even numbers form a sequence as well. Another word for a sequence is progression. Let's look at a few types of progressions in mathematics. The most common one is the arithmetic progression. So here we have a sequence of numbers 1, 4, 7, and 10. And this sequence is generated by adding 3 to the previous number. So add 3 to 1, you get 4. Add 3 to 4, you get 7, and so on. Okay, you get an infinite sequence here. This number which gets added to each term is known as the common sum. and it is a constant. In this case, the sequence has a common sum of 1. It's the sequence of whole numbers. Now, after arithmetic progression, we have the geometric progression. Here we have a sequence of numbers 110, 210, 440, and so on. Excuse me, 220. So the pattern here is that each preceding number gets multiplied by 2. This 2 is known as the common ratio. And again, we see that in this sequence, the common ratio is constant. By changing the first number, the initial term, and the common ratio, you can get a variety of sequences. Now, this common term can be a whole number like 2. It can even be a fraction or a decimal number. And the same applies to the arithmetic progression as well. Instead of adding 3 to each number, you can add 0.5. You can even add irrational numbers like square root of 2. Okay. And the same applies here too. Instead of multiplying by 2, you can multiply by square root of 2, and so on. So I now have a question for you guys. What is this? What type of sequence do you see here? The chat is very quiet. Yeah, that's right. The iPad got it right. But I don't know who iPad is, because iPad did not name themselves properly. So yeah, this is the arithmetic and geometric progression, or arithmetico-geometrical progression. So let's have these 3 progressions in mind, and then train ourselves in recognizing some of the sequences of numbers. Now, there are some rules or pointers that can help us to save some time when recognizing the patterns in a sequence. A good way to start is to subtract consecutive terms. If the difference between the terms come as a constant number, then you have an arithmetic progression. The next thing is to divide consecutive terms. And then if that comes as a constant number, then you have a geometric progression. Checking for arithmetico-geometric progression takes several steps. You'll have to start by finding the difference, and that difference will not be a constant. It will be increasing. You might have to divide the consecutive terms and find that that leads to a sequence of numbers which represent an arithmetic progression. You can also check for convergence or divergence or periodicity. What I mean is, if you take a sequence as simple as 1, 2, 3, 4, 5, and so on, we can see that it's diverging. It continues to increase forever. It will go on until it reaches infinity. Sometimes you have a sequence of numbers that gets progressively smaller. You can have something like 4, 2, 1, 0.5, 0.25, 0.125. So here each number gets multiplied by 0.5, or it gets divided by 2, and it converges. Or it can be periodic, and by that it can repeat. The terms can repeat. If there's a repetition, then the pattern is very clear. Okay. And you'll find that these numbers, these sequence of numbers that's given to you, it need not be a single line of numbers. They can be arranged in an array, forming a shape, be like a square shape or a triangle or rectangle, whatever. So you might even consider adding numbers along a column or a row, or if the numbers are within shapes, adding and subtracting those numbers. Those are some things that you can do. But in the end, it comes to a trial and error method. There is no magic formula. There is no shortcut that can help you to find the pattern of any given sequence or arrangement of numbers. It requires a lot of creativity once you finish trying out the common methods. In addition to a pure numerical sequence, that's like a progression of numbers, you can have hybrid sequences. Okay. And these could be where numbers and shapes combine to form a pattern, or it could be numbers and letters of an alphabet, like an alphanumeric sequence. Now let's take this example. Okay, I'll give you guys a couple of minutes to find out the missing number. Now, this is clearly a case of a hybrid sequence, because you not only have numbers representing a pattern, you also have shapes. You have 4 squares here and 4 numbers within each square. Oh, pardon me, you have 5 squares here. Wow, I'm getting mixed responses. 3, 6. And I'm afraid I don't see the answer that is going to solve this problem. I see 1 person has found the answer. That's 2, 3, 4. Not bad. This is a little surprising that not everybody has found the answer. Because moments ago, I was just saying how you can find numbers within shapes. and you might want to add them up. Have you guys tried adding the numbers inside each square? Yeah, all right. There you go. So we can see that adding the numbers within each square yields the number 15. For instance, the first square, 5 plus 4 is 9, plus 3 is 12, plus 3 is 15. Okay. And we get the same everywhere. And you guys can stop spamming the chat now. Thanks. So the inside square, which is missing a number, should have the number 6, so that they also add up to 15. Good. So that's a pretty simple example of a hybrid sequence. Now let's look at something that's not so obvious. What about this one? There's only a single shape here, and that is of a hexagon, and the numbers are scattered, apparently in random. If you're still wondering about the previous puzzle, yes. The answer for this one is 6. So that 5 plus 3 plus 1, which is 9, plus 6 would give you 15. Okay. So we have now come to here. So if you don't have a pen and a paper with you, now would be a good time to grab those things. Okay, because this particular problem is not easy to be solved in your mind. I'm getting mixed answers here. 180, 86, 290. And there's a request for a hint as well. Well, this looks like a random arrangement of numbers. You could convert it into a sequence. You could arrange them in an ascending order, starting from the smallest to the largest. If you have a visual mind, you can see that starting from 2, you can draw a spiral, and that follows the numbers in an ascending order. Yeah. So once you get the numbers in a sequence, then you'll have to use some of the techniques that we saw earlier. Subtract the terms, divide the terms, see if you have a constant difference or a constant factor that each number gets multiplied by, or is it something more complex? Is it an arithmetical geometric progression? Huh? So this is the sequence of numbers that we saw before, right? Just written in ascending order. There is no common difference. And it's not a simple arithmetic progression. It's not a simple geometric progression. But what is going on here? So one thing you guys have to recognize or get used to recognizing is certain key numbers. For example, 128 or 32 or 8, for instance. Now what's common between the numbers 2, 8, 128, 32? So they were squares of 2. Now, once you recognize that 2 is 2 raised to 1, 8 is 2 raised to 3, okay, so on, it gives you a hint. Maybe there is an exponential behavior here. And in fact, we find that each term follows a pattern. Each term is a product of 2 terms. The first term is always 2, and the second term is the square of the sequence of whole numbers, starting from 1. 1 squared, 2 squared, 3 squared, 4 squared, and so on. Okay. So 182 is 2 times 9 squared. 9 times 9 is 81. 81 times 2 is 162. So the next number has to be twice 10 squared, which is 200. Okay. So that was pretty neat. So here in this particular example, you see that there is an element of an arithmetic progression here. Right? The numbers within the parentheses, within the brackets, 1, 2, 3, 4, 5, that forms an arithmetic progression. But it's not just that. That term gets squared. And not just that as well. And that square term gets multiplied by 2, like a geometric progression. So there's about 3 different ideas combined to create a sequence of numbers. So you have to keep this in mind, that the pattern that you're looking for might not be a simple pattern. It could be complex. All right. So I have this arrangement of numbers for you guys. Now, first question, do you recognize this? Yeah, somebody does. All right. So if you know what it is, then chances are you know how it is filled out. To those who don't know, don't cheat, don't look it up on the internet. Try to find a pattern that can help you to fill the missing squares. Yes, it is a Pascal's triangle. If you know how it is generated, good. If you don't know, excellent. Try to discover what the pattern has to be here. If you know that this is a Pascal's triangle and how it is populated, then go find out where Pascal's triangle is used. Why is it useful? I'll give you guys 1 more minute. Okay. Did anyone figure out the pattern that will help you to complete this pyramid or triangle? Aha, looks like Arjuna has cracked the code. Each number is the sum, the addition of the two numbers above it, directly above it. And let's see how that looks like when filled out. So on the left slope and the right slope, including the apex, we have the number 1. All right. Forget the first row and the second row. Now look at number 2, the third row in the middle. Now that too is got by adding the 2 ones above it. Now what about the 3s? The row below. The 3 comes from the addition of 1 and 2. And the 4 comes from the 4 in the 5th row comes from the addition of 1 and 3. And the 6 comes from the addition of 3 and 3. So following this pattern of addition, you can create an infinitely large pyramid or triangle. As some of you have found out and declared in the chat, it's used in probability. Specifically, it is the coefficient of the expansion of a general algebraic binomial expression. It's a plus b, the whole raised to n. Very neat. We're not interested in the application of the Pascal's triangle, but rather the recognition of patterns. Since this is a popular mathematical pattern, it's included here. Okay, so it's now about 7 o'clock, and I have one online quiz, a simple quiz ready for you guys. I can share that quiz with you by sending the link in chat. Okay, just have to give your name and then take the quiz. It's only 6 questions, and we will consider this quiz as a break. Okay. So you guys can take up to about 15 minutes. I'm going to share the link with you guys in the chat right now. Okay, so there is the link. I will also share it in the WhatsApp group. It's a simple quiz. Go ahead and give it your best shot. And we will discuss them at 7:15. If you have any trouble accessing the quiz, please let us know. You guys have about 10 minutes left. Are you able to access the quiz? Okay, good. Please carry on. We shall reconnect at 7:15. Hi guys, we have a couple of minutes left. We will resume our discussion soon. If you have finished the quiz, stretch your legs, give rest to your eyes, drink some water. And think of the best way, a concise explanation for your answers. Because I'll be asking for it soon. And by answers, I mean an explanation. I don't just want to know the number that's going to complete the pattern, but continue the sequence. So think of ways to explain your answers in as few words as possible. Okay, it's 7:15. I hope all of you are back. And have completed the quiz. So the first question was pretty easy, wasn't it? What is that image an example of? Yeah, that's right. It was a tessellation. Good. Does anyone need more time for the break, or can we continue? Okay, we'll give 2 more minutes for anyone to complete their business. Until then, I'll just give you guys some idea of how people have done in the quiz. So I'm looking at the test report, the quiz report. Not bad. So the person who took the least amount of time, 1 minute and 8 seconds, he got a score of about 15%. Okay. And someone else took the longest time for the quiz, 8 minutes and 34 seconds. That person also got about 15%. Okay. Looks like a lot of you have got about 15%. Highest happens to be about 66%. So nobody got all correct. That's fine. All right. So let's look at this one. Okay. Yeah, that's fine. The number is 3. Okay. Now give me the explanation in one single message, in one line, if possible. I don't want a series of 3s in the chat. I would like one sentence explaining why the answer is 3, or any other number for that matter. So Arvind says that the following number is the a difference between the previous number. So the third square is 3, because that's a difference between 5 and 2. Then how do you explain 29 and 34? Is there a pattern? I see a variety of responses in the chat, and none of them is convincing. Shyam Ganesh seems to be on the right track. He says that 2 squared plus 5 squared equals 29. And isn't that right? Yeah, 2 squared is 4, 5 squared is 25. 4 plus 25 gives you 29. And if you have to go by the same pattern, okay, that is the number below, the number in the second row is the sum of the squares of the 2 numbers above it. And 34 must be square of 2 numbers, one of which is 5. So 5 squared is 25. So the other number must be the square root of 9. Therefore, 3. So one problem that you can face is assuming that what we see here is a sequence of numbers, right? That it's 2, 5, some missing number followed by 29 and 34. But there is a reason that they have been put in squares and arranged in this way. We should never be narrow-minded. So looking at this as an array of numbers, as an arrangement, then we can look at vertical relationships as well. So it's not only a linear, like a straight line going from 2, 5, missing number 29, 34. Look at it as an arrangement, then we can see that 29 is the sum of the squares of the 2 numbers above it, namely 2 and 5. And thus we can arrive at the answer. Okay. Is there anyone who is finding this difficult? Should I repeat the explanation? Is there anyone who did not understand this? Okay. I'll take that as a positive response and move to the next one. All right, this one, guys. What's going on here? All right, I see some explanations. Okay. The difference between the first two numbers is 6, and the next is consecutively multiplied by 2. I don't understand that statement. 8 plus 16 is 34. Yes. How does that help us? I guess they're saying then 10 plus 34 would be the next digit. That's plausible. But then again, the question is, how do you decide what the next number would be? It would be 10 and 34. Sum of 10 and 34. And no. Okay. Now that's one way, but it's not very strong. I'll tell you why. Because you've found one relationship. That's it. You found 8 and 16. Adding that up will give you 34. But in this, you have not used the value 10. There's only one instance of this relationship. It's not a repeated pattern. If we can come with a pattern, okay, a relationship that gets repeated at least 2 times, then we can be assured that, okay, then this pattern will continue. But if you're looking at just one relationship, then there is no assurance that that is what the author had in mind, or that relationship will continue as a pattern. I can see that a lot of people are providing explanations. Okay, one of which is find the difference between 2 consecutive numbers and multiply it by 3 to get the next number. All right. So there are a couple of different ways of expressing this pattern, one of which is given here. Okay, you can take each number, multiply it by 3, and subtract 14 to get the next number. So let's check that here. 8 times 3 is 24. Minus 14 will give you 10. 10 times 3 is 30. Minus 14 will give you 16. Sixteen times 3 is 48. Minus 14 will give you 34. And doing so, you will find that the next number has to be 88. Now, I know some of you arrived at the same answer, 88, but you found a different pattern as well. So there are two lessons to take home here. One, that you need to look for a repetition of a relationship, not a single relationship. For example, yes, 8 plus 16 does give you 34, but that single relationship cannot be claimed to represent the pattern. It's very weak. It's a weak argument. However, when you say that each number is multiplying, it's got by multiplying the previous number by 3 and subtracting 14, that you can apply it for each term, for 3 terms, 10, 16, and 34, and verify it. So that relationship can be verified 3 times. Now this has a stronger claim of becoming the pattern. Yeah. So one other way of expressing this pattern is to see each number as an exponent of 3, which gets added to 7. For example, the first term would be 3 raised to 0 plus 1. Okay, that will be 1 plus 7, which gives you 8. The next term would be 3 raised to 1 plus 7. That would be 3 plus 7, making it 10. The next term would be 3 squared plus 7. That would be 9 plus 7, which is 16. The next term would be 3 cube plus 7. That would be 27 plus 7, which gives you 34. So that is another way of explaining this sequence of numbers. That's the second lesson. First lesson, you need to identify a relationship that's repeated at least 2 times. Okay, not just a single relationship. For example, yes, 8 plus 16 does give you 34 here, but that does not include 10, and we cannot see this relationship repeated. So it is a very weak claim for a pattern. Okay. And secondly, there can be multiple explanations for a pattern. So one is this, what's given here. Multiply each number by 3 and subtract 14. You will generate the sequence of numbers. You can also see it as 3 raised to 0 plus 7, 3 raised to 1 plus 7, 3 raised to 2 plus 7, and so on. So that's another explanation for a sequence, for the sequence of numbers. All right, what about this one? What is the pattern here? Shyam Ganesh has the right answer. Difference of numbers arranged diagonally remains the same. Which diagonal are we looking at? Because there are, you can imagine 2 diagonals. Yeah, from left to right. Okay, so if you look at these numbers on the starting from 19, okay, so 19, 21, 23, 25. That sequence of numbers have a common difference of 2. It's a simple arithmetic progression. What about the next layer? That's 2, 6, and 10. The common difference is 4. The next number, next layer, 27, 32, 37, and 42. So the common difference here is 5. So what I'm saying is, if you look at the numbers diagonally from left to right, okay, from top left to bottom right, you get arithmetic progressions. And here in this image, if you go from top left to bottom right, 19, 21, 23, 25, the difference between each number is 2. The next row, next layer, you have 2, 6, 10, the difference is 4. The next layer, the difference is 5. Okay. The next layer, we don't know, there's a missing term, but we can guess that it has to be an arithmetic progression. And whatever number is there must be the midpoint between 11 and 23, which happens to be 17. Okay. Then you can see the next layer, 20, 27, 34, 41. The difference is 7. The next one, it's 9. And the next one, the next one, it's 8. And the last one, it's 9. So yeah, you're moving diagonally downwards from the left to the right. And you find that the numbers form an arithmetic progression. Okay, that's is this clear to everybody? Can we move on? Does Praveen need another explanation? So I'll quickly repeat myself. So in this arrangement of numbers, we look at different sequences of numbers. If you follow this line shown here, this arrow, and you're moving diagonally from top left to bottom right, 19, 21, 23, 25. That forms an arithmetic progression. Okay. Next one is 2, 6, 10. That's another arithmetic progression. So all these layers of numbers form APs, arithmetic progression. All right. Move on to pure numeric sequences. Just numbers. Now this can get are quite difficult. Okay. Let's look at a few examples. Yeah, we have this. Found this in your quiz as well. What is the answer and the explanation for it? So one explanation, the number plus itself plus 1 and the number plus itself minus 1 and so on. So a number plus itself has a simple a mathematical expression, can be simplified as being multiplied by 2. So what Vishnu is trying to explain is that 25 is 12 times 2 plus 1, and 49 is 25 times 2 minus 1. In other words, each term alternates between adding or subtracting 1 from the previous term after multiplying it by 2. Okay. So to understand such sequences, we have to look at alternating numbers. Okay. And then see if there is a pattern within a subset of the sequence of numbers. So here you divide them as the blue numbers and the red numbers. Okay. And then you can see all the red numbers are actually the previous number times 2 plus 1. That's great. It's wonderful. You have a sequence. You have a pattern. You have this pattern, this relationship repeated 3 times. That's a strong statement, a case for this pattern. However, how do we use this information to find the missing number? It does not help us. But we need not worry. We can use the blue numbers and see if they follow a pattern. And indeed they do. So the blue numbers are found by multiplying the previous number by 2 and subtracting 1. So 49 is 25 times 2 minus 1. 197 is 99 times 2 minus 1. 395 is 197. I'm sorry. And then the next number must be 395 times 2 minus 1. Okay. And that will give us the answer as 789. So one, you can call it a trick, or you could call it one approach, is to divide a sequence into 2 sequences of alternating numbers, and then see if they have any pattern, distinct pattern in themselves. All right, what about this one? Okay. See a few responses here. The alternate numbers form multiples of 7 in steps of 2. I don't know what that means. Multiples of 7. 7 times 1, 7 times 2, 7 times 3 is missing because 7 times 3 is 21. I don't see that here. I see 7 times 4, which is 28. I see mixed responses, 56, 42, 35. Wait, are you... Okay. Sham Ganesh says odd terms are being added by 3 and even terms are being multiplied by even numbers starting from 2. Let's see that. Yeah, so there are 2 sequences here. That much is clear. One is a simple arithmetic sequence. 34, 37, 40, and 43 forms a simple arithmetic progression with a common difference of 3. Okay, 34 plus 3 gives 37, 37 plus 3 gives 40, 40 plus 3 gives 43. That is fine. Now the numbers in between, 7, 14, 28, that sequence needs to be unlocked. Kautik Khanna has a nice pattern. He sees that 7 times 2 gives 14, 14 times 2 gives 28. So the next number should be 28 times 2. That is a very good explanation. So 56 seems to be the right answer, doesn't it? Although some people insist that 42 is the answer. All right, let's break this down. Then again, first we separate the alternating numbers. Here, the blue numbers and the red numbers. Blue numbers are easy. They're simple arithmetic progression. Now the red numbers, one way to look at it is to see them as the multiple of the previous red number. Okay. Multiplying that by 2. The same can be further expressed as this. Okay. And you have seen this sequence before. Yeah, and expressing it in this form also gives us 56. Because the missing term would be 7 times 2 raised to 3. That is 7 times 8, which is 56. So essentially it is each red term gets multiplied by 2, starting from 2 raised to 0, which is 1. So good. Does anyone need more explanation on this one? Do you want me to repeat? Okay, cool. Then we can proceed. Oh, what about this one, fellas? This was not in the quiz. I'm guessing you're all working very hard to find the pattern here. This one kind of is a tricky question, because what we do here is going to be very different from what we have been doing so far. Oh, somebody says 640. And then I see lots of 660s. Okay. So let's break this down. The first thing that you guys have to notice is that the middle number of each term alternates between 8 and 6. Yeah, I know. Even before you subtract the terms and see if it's an arithmetic progression, or divide them to find if it's a geometric progression, this detail should stand out to your eyes. Because sometimes the shortcut can actually help you. Now we see that there's an alternation of the middle digit between 8 and 6. So you can expect, okay, that the next number should have 6 as the middle digit in the 100th place. Yeah. And if you investigate a little more, you will see that the other two numbers are not random. Okay. The blue numbers add to give you the number in the middle. 1 plus 7 gives you 8. 2 plus 4 gives you 6. 3 plus 5 gives you 8. 4 plus 2 gives you 6, and so on. Okay, that's very interesting. That's another detail that you should be able to find after spending a little time on this. Now, how does that help us? Can that help us find the other number? Sure, the middle number has to be 6, and the other two numbers should add up to 6. But what are those two other numbers? Yes, the first digit of each term is an arithmetic progression. You can say that it's 1, 2, 3, 4, 5. In fact, that should be the first thing anyone would notice, right? Instead of the alternating 8 and 6. Doesn't matter. So here, this sequence is a combination of 3 ideas. 1, the first number in each term is a sequence of whole numbers, 1, 2, 3, 4, 5. Okay. The middle term, the middle number in each term alternates between 8 and 6. And then finally, the first number and the last number in each term add to give the middle number. So therefore, combining all those ideas, we can see that the missing term, or the next term in the sequence, has to be 660. All right. Can this sequence go on forever? Is this an infinite sequence of numbers? It is not. That's right. So this is a sequence which converges. Okay, it's a converging sequence, so it's a finite sequence. It abruptly ends here. Okay. Now, you're coming close to the end of the session. You have 5 minutes left. And your worksheet, the workbook has been sent to everybody. And there are more problems for you to solve there. These are mathematical brain teasers, similar to what we did last week. However, these are very arithmetic, more mathematical than about real life problems. And we saw numeric sequences. We saw numeric sequences combined with geometric shapes. You can even have alphanumeric sequences. Okay. For example, this one, which we shared in the WhatsApp groups as a brain teaser number 2. Do you guys know how to solve it? So I'm getting mixed responses. I'm getting L, K, Q. To go about and solve this, you have to use what is known as the letter substitution. Okay, so you substitute each letter with a number, and there are many ways to do this. You can substitute each letter with an even number, but the easiest, the simplest one is by the place they hold in the English alphabet. That means A is the first letter, so you give it you substitute it with a number 1. B is the second letter, you substitute it with the number 2. So if you do this, you can convert this alphanumeric and geometric sequence into a numeric sequence. You'll have 3 numbers at the vertices of a triangle and 1 number inside. And then you'll find that there is a simple relationship between those numbers for each triangle. And yeah, once you follow this train of thought to the end, you will realize that the answer is indeed K. All right. And this number substitution cipher is also used in cryptography, sending secret messages. You can also have pure geometric sequences, okay, without any numbers, and still have patterns. Like over here. Here we have an array of shields, and each shield has a design on it. Then you're expected to predict what the missing pattern is, the missing design. Now, when you look at this, you can immediately recognize that the missing shape should have black color, because each row has one shape, which is black. And each row has one of the three different shapes. Yeah, therefore it has to be black and a flower. Now, something else to notice is that one shape in each row gets turned upside down. In the first row, we have the three-leaved clover. Right? That's upside down. In the second row, the flower is upside down. The third row, the cross is upside down. So the missing shape should be a black flower upright. Yeah, just pretend that the flower is black. Okay, then you have the answer for you. So in the worksheet, you have more of such problems like this one. Okay. And these things, they're not immediately clear as to how they would form a pattern. It will take some time to analyze and get the relationship. Okay. So have fun at home, solving the different types of sequences of shapes, numbers and letters, shapes and letters, and there's lots more to discover on the internet. And you can also have fun creating cryptic messages. Okay. And that brings us to the end of the session. Level 2 of Brain Excel, pattern recognition. This is not the end of the journey for Brain Excel, because there is another session on spatial reasoning, but we have not scheduled it yet. So if we scheduled it, maybe we will see you guys that time. Next workshop is something different. We're going to move on to a new theme, developing Android apps, the apps that you have in your mobile phones. Okay, you have apps for different purposes. You have apps for navigation, like your Google Maps. You have apps for voice recognition. You speak and then it turns and makes it into a text. You have games, which are apps. Okay. You can plan your journey. You can book hotels. You can book movie tickets. You can shop. All of these things are powered by Android applications or apps. So next Wednesday, between 6 and 8 p.m., we'll have an Android app workshop. Okay. It will be in two parts. The first part is on Wednesday. Okay. More details will be given in the WhatsApp group. I hope you guys had fun today and enjoyed pattern recognition. I hope to see you guys in the future for another workshop. You guys have a good night and have fun. Be safe, stay healthy. Get good exercise for your body and mind. Bye-bye. Thanks to you. Good night.